Something horrible is happening in CERN. Right now, buried beneath the scenic landscapes of France and Switzerland, the world's most powerful particle accelerator in history, the Large Hadron Collider, is once again colliding particles in record fashion, at the highest energies and with the greatest collision frequencies of all time. Record numbers of collisions at record high energies are bringing us further in our hunt for the fundamental nature of the universe and our understanding of the elementary building blocks of matter. But despite these successes, in a recent shocking revelation, CERN official has revealed that during a test with unprecedented energy levels, something terrible happened at CERN, and no one can explain. Could this unexpected discovery unlock more secrets of our vast universe? Or will it provide a new physics? Join us as we dig deep into the new findings that baffle even the most seasoned researchers. But before we get to that, let's take a look at particle physics. Particle physics has two sides to it, a theoretical side and an experimental side. On the theoretical side, there's the Standard Model, which is arguably the most successful physical theory of all time. And then there are ideas for what lies out there beyond the Standard Model. The Standard Model is a predictive framework for understanding the particles in our universe, what their properties are, how they interact and decay, and what we expect the results of any specific laboratory experiment to yield. There are also extensions to the Standard Model, possible ways to go beyond it, that have been explored at length over the past 50-plus years. The Standard Model tells us what particles there are and how they couple to one another, and allows us to determine not only what interactions are possible versus forbidden, but what the relative probability of each potential outcome is. There are many ways to put the Standard Model to the test, but arguably the most effective is to collide two particles moving at the highest equal and opposite velocities as possible, over and over, as many times as you can, and detect what comes out. By measuring the debris of this collision precisely enough, you can reconstruct what happened at every step of the way. The LHC at CERN is the most powerful particle accelerator in Earth's history, capable of reaching energies of approximately 7 TeV per particle. That equates to accelerating protons to 299,792,455 mass apiece, just 3 ms shy of the maximum achievable speed in the universe, the speed of light. For years, since it first turned on in 2008, the LHC has been colliding as many protons with other protons by bunching them together, circulating them in both the clockwise and counterclockwise directions in its large ring, timing their motions so that the bunches intersect at particular collision points, where large detectors are awaiting those collisions, and they measure at a series of distances the energy, momentum, charge, spin, and other properties of the particles that arise in the aftermath of that collision. By measuring what comes out of those collisions and comparing those experimental results with the theoretical predictions that arise from both Standard Model-only scenarios as well as beyond the Standard Model scenarios, you can determine how well the Standard Model, by itself, fits what you've observed. Any departures from it, so long as they're robust enough, are something that will make the entire community sit up and take notice. But even before the Large Hadron Collider turned on for the first time, we knew that there must be more to the universe than the Standard Model gives us. Roughly speaking, the Standard Model separates fundamental particles into two types, fermions and bosons. Fermions are the bricks of matter. Two kinds of fermions, called up and down quarks, for example, are bound together into protons and neutrons. If those protons and neutrons glom together and find an electron or electrons to orbit them, they become an atom. Bosons, on the other hand, are the mortar between the bricks. Bosons are responsible for all the fundamental forces besides gravity, electromagnetism, the weak force, which is involved in radioactive decay, and the strong force, which binds nuclei together. To transmit a force between one fermion and another, there must be a boson to act as a messenger. For example, quarks feel the attractive power of the strong force because they send and receive bosons called gluons. This framework unites 3 out of 4 fundamental forces and tamed an unruly zoo into just 17 elementary particles. During 50 years, the Standard Model remains superbly successful. Even under stress tests, it correctly predicts fundamental properties of the universe, like the magnetic properties of the electron and the mass of the Z boson, to extremely high accuracy. But despite its accuracy, physicists have their pick of questions the Standard Model doesn't answer. For instance, we discovered that neutrinos and antineutrinos weren't massless and didn't remain the same species of particle, but rather had a non-zero rest mass and would oscillate from one flavor, electron, mu, tau, to the others, particularly when they interacted with matter. We discovered that dark matter exists, and were able to rule out all of the Standard Model particles, as the Standard Model predicts them, as viable candidates for it. We discovered the accelerated expansion of the universe, which we attribute to a new form of energy, dark energy, which again cannot be explained by anything within the Standard Model. We knew that there was no CP violation in the strong interactions, only in the weak interactions, despite the fact that the Standard Model allows for both. If a spinning particle decays, the antiparticle counterpart that spins in the opposite direction is observed to behave differently under the weak interactions, but not the strong interactions, and nobody knows why. And finally, we live in a universe made predominantly of matter and not antimatter. But the laws of physics do not have enough of an asymmetry between them to create the matter-rich universe we inhabit today. In short, in many ways, there are many things we still don't know about the universe. But at particle colliders, where we take matter, and sometimes antimatter, smash it together at high energies, and observe the particle debris that comes out, there have been no observations or measurements that have stood the test of time that run counter to the Standard Model's predictions. When the LHC began colliding particles, it was the last good hope for many theoretical ideas that had been bandied about as plausible explanations for what could be out there beyond the Standard Model for many decades. Such a giant leap came in 2012 when researchers using data from the LHC discovered a particle called the Higgs boson. In the process, they answered a nagging question. Where do fundamental particles, such as the ones that make up all the protons and neutrons in our bodies, get their mass? A half-century earlier, theorists had cautiously dreamed the Higgs boson up, along with an accompanying field that would invisibly suffuse space and provide mass to particles that interact with it. When the particle was finally found, scientists celebrated with champagne. A Nobel for 2 of the physicists who predicted the Higgs boson soon followed. But now, more than a decade after the excitement of finding the Higgs, there is a sense of unease because there's still much that's unknown about the Higgs boson, and unlocking its secrets may help scientists understand the universe at its smallest scale and some of the biggest mysteries in the cosmos. Based on LHC's data, the Higgs had a mass of 125 giga-electron volts, which was orders of magnitude smaller than what physicists had thought it should be. To be perfectly clear, the Standard Model doesn't actually predict the value of the Higgs mass. For that theory to work, the number has to be derived experimentally. But back-of-the-envelope calculations made physicists guess that the Higgs would have an incredibly large mass. So once the champagne was opened and the Nobel Prizes were handed out, the question loomed: why does the Higgs have such a low mass? In another, and initially unrelated problem, the strong force isn't exactly behaving as the Standard Model predicts it should. In the mathematics that physicists use to describe high-energy interactions, there are certain symmetries. For example, there is the symmetry of charge, the symmetry of time, and the symmetry of parity. In all experiments performed to date, the strong force appears to obey the combined symmetry of both charge reversal and parity reversal. But the mathematics of the strong force do not show that same symmetry. No known natural phenomena should enforce that symmetry, and yet nature seems to be obeying it. So, what gives? A pair of theorists, Raffaele Tito Dagnolo of the French Alternative Energies and Atomic Energy Commission, CEA, and Daniele Teresi of CERN, thought that these two problems might be related. In a paper published in the journal Physical Review Letters, they outlined their solution to the twin conundrums. Their solution: the universe was just born that way. They invoked an idea called the multiverse, which is born out of a theory called inflation. Inflation is the idea that, in the earliest days of the Big Bang, our cosmos underwent a period of extremely enhanced expansion, doubling in size every billionth of a second. Physicists aren't exactly sure what powered inflation or how it worked, but one outgrowth of the basic idea is that our universe has never stopped inflating. Instead, what we call our universe is just one tiny patch of a much larger cosmos that is constantly and rapidly inflating and constantly popping off new universes, like foamy suds in your bathtub. Different regions of this multiverse will have different values of the Higgs mass. The researchers found that universes with a large Higgs mass find themselves catastrophically collapsing before they get a chance to grow. Only the regions of the multiverse that have low Higgs masses survive and have stable expansion rates, leading to the development of galaxies, stars, planets, and eventually high-energy particle colliders. To make a multiverse with varying Higgs masses, the team had to introduce two more particles into the mix. These particles would be new additions to the standard model. The interactions of these two new particles set the mass of the Higgs in different regions of the multiverse. And those two new particles are also capable of doing other things. The newly proposed particles modify the strong force, leading to the charge parity symmetry that exists in nature. They would act a lot like an axion, another hypothetical particle that has been introduced in an attempt to explain the nature of the strong force. The new particles don't have a role limited to the early universe either. They might still be inhabiting the present-day cosmos. If one of their masses is small enough, it could have evaded detection in our accelerator experiments, but would still be floating around in space. In other words, one of these new particles could be responsible for the dark matter, the invisible stuff that makes up over 85% of all the matter in the universe. It's a bold suggestion, solving two of the greatest challenges to particle physics and also explaining the nature of dark matter. Could a solution really be this simple? As elegant as it is, the theory still needs to be tested. The model predicts a certain mass range for the dark matter, something that future experiments that are on the hunt for dark matter, like the underground facility the super cryogenic dark matter search, could determine. Also, the theory predicts that the neutron should have a small but potentially measurable asymmetry in the electric charges within the neutron, a difference from the predictions of the standard model. Unfortunately, we're going to have to wait a while. Each of these measurements will take years, if not decades, to effectively rule out or support the new idea. But besides the idea of a multiverse, scientists also have been looking very hard at a number of other well-motivated scenarios that have the theoretical potential to address these puzzles. Until recently, most of these papers relied on the concept of supersymmetry, abbreviated to the friendlier SUSY. Under SUSY, fermions and bosons are actually mirror images of one another, so that every fermion has a boson counterpart, and vice versa. The photon would have a superpartner dubbed a photino in SUSY parlance, while an electron would have a selectron. If these particles were high in mass, they would be hidden, unseen unless a sufficiently high-energy collision left them as debris. In other words, to create these heavy superpartners, physicists needed a powerful particle collider. It might seem strange and overly complicated to double the number of particles in the universe without direct evidence. SUSY's appeal was in its elegant promise to solve two tricky problems. First, superpartners would explain the Higgs boson's oddly low mass. The Higgs is about 100 times more massive than a proton, but the math suggests it should be 100 quadrillion times more massive. Susie's quick fix is this: every particle that interacts with the Higgs contributes to its mass, causing it to balloon. But each superpartner would counteract its ordinary counterpart's contribution, getting the mass of the Higgs under control. The second promise of Susie: those hidden particles would be ideal candidates for dark matter. Susie was so nifty affixed to the Standard Model's problems that plenty of physicists thought they would find superpartners before they found the Higgs boson when the LHC began taking data in 2010. Instead, there has been resounding silence. Not only has there been no evidence for Susie, but many of the most promising scenarios where Susie particles would solve the problem of the Higgs mass have been ruled out. At the same time, many non-collider experiments designed to directly detect the kind of dark matter you'd see if it were made up of superpartners have come up empty. Many younger researchers are less attached to the idea. For them, Susie would have been a really pretty story. Since they came in after it, it's just kind of like this interesting history. By contrast, some theorists are now directing their search away from particle accelerators and toward other sources of hidden particles. Masha Baryakhtar, a theorist at the University of Washington, uses data from stars and black holes. According to Baryakhtar, these objects are really high density, often high temperature, and so that means that they have a lot of energy to give up to create new particles. In their nuclear furnaces, stars might produce loads and loads of another dark matter candidate called the axion. There are experiments on Earth that aim to detect such particles as they reach us. But if a star is expending energy to create axions, there will also be telltale signs in astronomical observations. Baryakhtar hopes these celestial bodies will be a useful complement to detectors on Earth. Hundreds of scientists around the world are working together to understand one of the most powerful emerging technologies before it's too late. Other researchers are finding ways to give new life to old ideas like Susie. In fact, some promising versions of Susie that account for dark matter are completely untested. After initial investigations did not find Susie in the most obvious places, many researchers began looking for long-lived particles, or LLPs, a generic class of potential particles that includes many possible superpartners. Because detectors are primarily designed to see particles that decay immediately, spotting LLPs challenges researchers to think creatively. The two general-purpose detectors at the LHC Atlas and CMS are a bit like onions, with concentric layers of particle-tracking hardware. Most of the initial mess from proton collisions, jets, and showers of quarks decays immediately and gets absorbed by the inner layers of the onion. The outermost layer of the detector is designed to spot the clean, arcing paths of muons, which are heavier versions of electrons. If an LLP created in the collision made it to the muon tracker and then decayed, the particle trajectory would be bizarre, like a baseball hit from first base instead of home plate. A recent search by the CMS collaboration used this approach to search for LLPs, but didn't spot any evidence for them. Researchers scouring the data often don't have any faith that any particular search will turn up new physics, but they feel a responsibility to search all the same. But searching for new particles isn't just a matter of being creative with the hardware, it's also a software problem. While it's running, the LHC generates about a petabyte of collision data per second, a veritable fire hose of information. Less than 1% of that gets saved, explains Ben Nachman, a data physicist at Lawrence Berkeley National Lab. We just can't write a petabyte per second to tape right now. Dealing with that data will only become more important in the coming years as the LHC receives its high luminosity upgrade. Starting at the end of the decade, the HL-LHC will operate at the same energy, but it will record about 10 times more data than the LHC has accumulated so far. The boost will come from an increase in beam density. Stuffing more protons into the same space leads to more collisions, which translates to more data. As the frame fills with dozens of collisions, the detector begins to look like a Jackson Pollock painting, with splashes of particles that are impossible to disentangle. To handle the increasing data load and search for new physics, particle physicists are borrowing from other disciplines, like machine learning and math. One of those projects involves applying optimal transport theory, an area of mathematics concerned with moving stuff from one place to the next, to particle detection. The field traces its roots to the 18th century, when the French mathematician Gaspard Monge was thinking about the optimal way to excavate Earth and move it. Conventionally, the shape of a particle collision, roughly the angles at which the particles fly out, has been described by simple variables. But using tools from optimal transport theory, scientists hope to help detectors be more sensitive to new kinds of particle decays that have unusual shapes and better able to handle the HL-LHC's higher rates of collisions. In addition, the energy of particle colliders as measured by the combined energy of two colliding particles has risen over the decades, opening up new realms of physics to explore. Indeed, there are many ways that we genuinely believe physics must, somehow, go beyond the standard model. For example, gravity is not treated as a quantum interaction, but rather as a classical, unchanging background by the standard model. Neutrinos are predicted to be massless by the standard model, and there's no dark matter nor dark energy. The standard model doesn't explain everything we see about our universe, and we fully anticipate that, at some level, there may be additional fields, particles, interactions, dimensions, or even physics from beyond our observable universe that could be affecting us. Back in 2017, the LHC surpassed a major milestone when they had put over 200 petabytes of data permanently into its tape libraries. To put this amount of data into perspective, 1 petabyte of data is equivalent to around 250,000 movies. But what are they looking for in all this data anyway? They noticed something going on with a particular kind of quark. As told, the standard model describes nature on the smallest of scales, comprising fundamental particles known as leptons, such as electrons, and quarks, which can come together to form heavier particles such as protons and neutrons, and the forces they interact with. There are many different kinds of quarks, some of which are unstable and can decay into other particles. The new result relates to an experimental anomaly that was first hinted at in 2014 when LHC beauty physicists spotted beauty quarks decaying in unexpected ways. Specifically, beauty quarks appeared to be decaying into leptons called muons, less often than they decayed into electrons. This is strange because the muon is in essence a carbon copy of the electron, identical in every way, except that it's around 200 times heavier. You would expect beauty quarks to decay into muons just as often as they do to electrons. The only way these decays could happen at different rates is if some never-before-seen particles were getting involved in the decay and tipping the scales against muons. While the 2014 result was intriguing, it wasn't precise enough to draw a firm conclusion. Since then, a number of other anomalies have appeared in related processes. They have all individually been too subtle for researchers to be confident that they were genuine signs of new physics. But tantalizingly, they all seemed to be pointing in a similar direction. The big question was whether these anomalies would get stronger as more data was analyzed or melt away into nothing. In 2019, LHCb performed the same measurement of beauty quark decay, again but with extra data taken in 2015 and 2016. But things weren't much clearer than they'd been 5 years earlier. Recent result doubles the existing data set by adding the sample recorded in 2017 and 2018. To avoid accidentally introducing biases, the data was analyzed blind. The scientists couldn't see the result until all the procedures used in the measurement had been tested and reviewed. Mitesh Patel, a particle physicist at Imperial College London and one of the leaders of the experiment, described the excitement he felt when the moment came to look at the result. "I was actually shaking. I realized this was probably the most exciting thing I've done in my 20 years in particle physics." When the result came up on the screen, the anomaly was still there, around 85 muon decays for every 100 electron decays, but with a smaller uncertainty than before. What will excite many physicists is that the uncertainty of the result is now over 3 sigma. Scientists' way of saying that there is only around a 1 in 1,000 chance that the result is a random fluke of the data. Conventionally, particle physicists call anything over 3 sigma evidence. However, we are still a long way from a confirmed discovery or observation that would require 5 sigma. Theorists have shown it is possible to explain this anomaly and others by recognizing the existence of brand new particles that are influencing the ways in which the quarks decays. One possibility is a fundamental particle called a Z-prime, in essence, a carrier of a brand new force of nature. This force would be extremely weak, which is why we haven't seen any signs of it until now, and would interact with electrons and muons differently. Another option is the hypothetical leptoquark, a particle that has the unique ability to decay to quarks and leptons simultaneously and could be part of a larger puzzle that explains why we see the particles that we do in nature. So, have we finally seen evidence of new physics? Well, maybe not. We do a lot of measurements at the LHC, so you might expect at least some of them to fall this far from the standard model. And we can never totally discount the possibility that there's some bias in our experiment that we haven't properly accounted for, even though this result has been checked extraordinarily thoroughly. Ultimately, the picture will only become clearer with more data. One thing particle physicists would really like in the future is more precision. The problem with protons is that each one is actually a bundle of quarks. Smashing them together is like a subatomic food fight. Ramming indivisible particles, like electrons and their antiparticles, positrons into one another, results in much cleaner collisions, like the ones that take place on a pool table. Without the mess, researchers can make far more precise measurements of particles like the Higgs. An electron-positron collider would produce so many Higgs bosons so cleanly that it's often referred to as a Higgs factory. But there is currently no electron-positron colliders that have anywhere near the energies needed to probe the Higgs. One possibility on the horizon is the future circular collider, known as FCC. It would require digging an underground ring with a circumference of 55 miles, 90 kilometers, 3 times the size of the LHC, in Switzerland. That work would likely cost tens of billions of dollars, and the collider would not turn on until nearly 2050. There are 2 other proposals for nearer-term electron-positron colliders in China and Japan, but geopolitics and budgetary issues, respectively, make them less appealing prospects. Physicists would also like to go to higher energies. Either way, every time we've gone to higher energy, we've discovered some new layer of nature. It will be nearly impossible to do so with electrons. Because they have such a low mass, they radiate away about 1 trillion times more energy than protons every time they loop around a collider. But under CERN's plan, the FCC tunnel could be repurposed to collide protons at energies 8 times what's possible in the LHC, about 50 years from now. It's completely scientifically sound and great. But could we get to higher energies faster? Well, the short answer is yes. In December, the alliteratively named Particle Physics Project Prioritization Panel, or P5, put forward a vision for the near future of the field. In addition to addressing urgent priorities like continued funding for the HL-LHC upgrade and plans for telescopes to study the cosmos, P5 also recommended pursuing a muon shot, an ambitious plan to develop technology to collide muons. The idea of a muon collider has tantalized physicists because of its potential to combine both high energies and, since the particles are indivisible, clean collisions. It seemed well out of reach until recently. Muons decay in just 2.2 microseconds, which makes them extremely hard to work with. Over the past decade, however, researchers have made strides, showing that, among other things, it should be possible to manage the roiling cloud of energy caused by decaying muons as they're accelerated around the machine. Advocates of a muon collider also tout its smaller size, about 10 miles, its faster timeline, optimistically, as early as 2045, and the possibility of a U.S. site, specifically Fermi National Laboratory, about 50 miles west of Chicago. There are plenty of caveats. A muon collider still faces serious technical, financial, and political hurdles, and even if it is built, there is no guarantee it will discover hidden particles. But especially for younger physicists, the panel's endorsement of muon collider R&D is more than just a policy recommendation. It is a bet on their future. Indeed, this could open a pathway to having this exciting, totally different frontier of particle physics in the US, and it's a frontier scientists are keen to explore. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.